Welcome back to Calculus 1. This is part 2 of our lecture on the derivative as a function. Part 1 of this lecture dealt with some computational problems calculating f prime of x with our limit definition. That was a sufficient amount of work. Within this part, we'll be looking at some conceptual problems relating to the derivative f prime of x. All right, we're going to jump straight into an example here. Recall within our first part, we took our time to understand the derivative f prime of x, or the derivative of whatever the name of our function is, as a function that takes an input as an x value, a real number, and then the output of the derivative function is the slope of a tangent line at a particular point. So we've been hammering that in. Again, it's not the only way to interpret derivatives, but it's a very useful way early on within the calculus sequence, especially in the beginnings of our course Calculus 1, to think of derivatives as representing slopes of tangent lines. Now this example is kind of simple in some sense. There's no elaborate calculations. There's nothing like the algebraic tricks, factoring, expanding, conjugates, none of that here. But it is difficult in its own right, since it starts to get into the conceptually challenging realm of calculus questions. Now, I'd like you to pause the video and give yourself maybe a minute to attempt this. I found kind of at this point in Calculus 1, students either get this question and how to answer it and the ideas needed, or they could stare at it for 4 hours and not understand what they need to kind of answer the question. So I'll give you a hint. Recall we have the question, what is a derivative? And we gave several answers to that. I don't want to tell you what answer to use right now, but one of them is appropriate or more appropriate than others here. Notice what the question wants, it gives you a graph of a function, but parts A through D are asking you if the quantities, which are all derivative values, are positive, negative, or zero. Think of that question, what is a derivative? We'll check in about a minute. All right, welcome back. Now, I could just tell you how to answer this, but hopefully there was enough of a hint. We have this question, what is a derivative? It's a fairly important question in my opinion. And there were several answers that we gave. And these are some standard basic interpretations appropriate for a first course in calculus within the calculus sequence. And they're basically the standard answers that a derivative is a slope of a tangent line. We can interpret it as an instantaneous rate of change of a function, or we can interpret it as a limit. Now for this question, since we're given the graph of a function, that's the clue or hint here, we probably want to think of a derivative with our first response. Think of a derivative as representing the slope of a tangent line. Now how do we go from the given information, the graph of the function, to what the question is asking us to determine is our positive, negative, or zero derivative values? Well, we're going to use our graph, look at each x-coordinate within the function notation for the derivative, and then look on the graph at that x-coordinate if the slopes of the tangent lines are positive, negative, or zero. So let's take a look at all those x-coordinates, 0.5, 2, 3, 5, and 6. Those are all the x-coordinates referenced in the derivative values there of g. Notice we have g prime of 0.5, g prime of 2, so on and so on. The input values there are the x values that we'll look at slopes of tangent lines. Okay, and really here, the question, the work is minimal, but it requires a lot of conceptual understanding. So we just visualize at each x-coordinate what the slope of the tangent line looks like. So we just look at the x-coordinate, see where that point is on the graph, and then draw a rough sketch of what the tangent line looks like. Here, it's enough just for our sketch to show us if our tangent line has positive slope, negative slope, or zero slope if it's horizontal. So we see here, going through the parts, part A, g prime of 0.5, we look at the graph where the x-coordinate is 0.5 or a half. We have that point up on the graph there above the x-axis, and at x equals 0.5, the tangent line has negative slope. So we would say for part A, g prime of 0.5 is negative because the tangent line has negative slope at the x-coordinate 0.5. All right, part B, that tangent line has positive slope. Part C, at least as best as I can draw it by hand, as I would in class with a chalkboard, which I miss very much. We see that the tangent line is horizontal, so it would have zero slope. Same thing at 5. So for part D, g prime of 5 is 0. The tangent line is horizontal there. And then at x equals 6, the tangent line is positive. The tangent line has positive slope there. And if you take a look at the question before we move on, again, always pause as needed. I try to keep the lectures short and to the point, 30 to 40 minutes, so that way you can go back and easily find ideas. But definitely pause to make sure you really get this. The work is minimal. Notice there's no algebraic calculations here, but we're replacing that with conceptual understanding. And that's kind of how we'll proceed in the course. A little bit later, things will be both computationally challenging and conceptually challenging, but we're not there yet. We're kind of doing one or the other. Within a little bit, a few sections, a little bit deeper into the textbook, the chapters, then both aspects, the computations and concepts, will both be challenging. All right, let's go ahead and move on. Within this topic, interpreting the derivative as a function, there's a new concept called differentiability, which is, at least within Calculus 1, an important property of functions. Earlier in our course, when we were talking about limits, we used limits to define continuity or a continuous function. And we're going to try to do that here, understand something about a function and its graph with the limit definition of a derivative. All right, so let's put up here, starting off, both versions for the limit definition of the derivative of a function at a point, what we would call f prime of a. All right, we have the limit as h approaches 0 version, which is what we first introduced. And then in the last lecture, this new version, but equivalent, is the limit as x approaches a. Similar expressions, both basically come from applying your basic slope formula to find the slope of the secant line, only the notation is different. All right, so we're stating this because we have here the derivative defined as a limit. So keep that in mind. What is a derivative? Well, now we can say a derivative is a limit. Keep that in the front of your mind as we go through this part. Okay, so at this point, we have enough to get into the definition for what a differentiable function is. This is a standard mathematical term. We'll define it first, and then we'll get into what it really means. What it really means, kind of at a basic, everyday level, for a function to be differentiable. Okay, so let's state the definition. We're going to say a function is differentiable at a. So a is some x-coordinate. So a function is differentiable at a point, is what we're defining here. And we have f denoting a function, a, an x-coordinate or x value. First off, it has to be in the domain of the function. Pretty much everything we're dealing with, x values at least, have to be in the domain of a function. We're Just stating that to be mathematically correct in case you're going the full distance through Calc 27. All right, now the definition here is that second sentence. We say that a function is differentiable at A if f prime of A exists. Now, f prime of A is the derivative of a function at a point. What would it mean for a derivative of a function at a point to not exist? Well, that's why I wanted you to think of a derivative as a limit. Now, this is probably the least frequently encountered response to what is a derivative, a limit, but it helps here, which is why it was the third of those three responses: slope of a tangent line, instantaneous rate of change, and a limit. The limit answer helps us understand the concept of differentiability. All right, so what is the connection here? A derivative is a limit. Well, we recall that some limits do not exist. And that's going to lead us to interpreting that a derivative, f prime of A, might not exist. This new definition would say it's possible for a function to be not differentiable if a certain limit, the limit definition of the derivative, does not exist. Notice how we're layering concepts on top of one another. So we mentioned this is conceptually challenging. Think back to how a limit might not exist. The simplest way is if the individual one-sided limits were different. Recall that when your limit from the right and left to a point are different, the two-sided limit or limit does not exist. So we'll be thinking of that through the next concrete example we'll be getting to momentarily. So definitely pause to copy this down into your notes or to take time to understand it. We're defining this property of a function being differentiable by referencing something about the limit definition of the derivative. When you're ready, unpause and we'll get to an actual simple function exhibiting the non-differentiability of a function. Are you ready? Let's get to a really simple function that is not differentiable at a point. Okay, so we're going to start first with what it means for a function to be not differentiable. Now, this is probably the standard example that I think every good calculus instructor should give, because it's arguably the simplest function that has this complicated property related to differentiability not existing for this function. So this function absolute value of x is not differentiable at 0. Why? Well, let's go back to the definition. All right, we're going to think first with the graph. I want to start to relate concepts together before we just get into mathematical definitions, which honestly some students, probably most, don't care about. Okay, so here's our graph of absolute value of x. Pretty simple. Kind of learned about that probably in your pre-calc course, probably even algebra. And it's a simple V shape. Now this graph is continuous. There's no breaks, gaps, or holes in it at 0. So this function, absolute value of x, is continuous at 0. And we're just claiming, really without any real proof, that it's not differentiable at 0. I want to follow up on why it isn't differentiable at 0. Let's go back to our definition. We said a function is differentiable at a point, 0 here, if f prime of A, here f prime of 0, exists. Now, flip that around. If a function is not differentiable, the derivative will not exist. All right, so let's, for this function, absolute value of x, look at the derivative at 0. So we'll be looking at the derivative of absolute value of x at 0. Now, just for ease of calculations, to quickly get to the point, we'll use our newest version for the limit definition, the limit as x approaches a version. This is just a little simpler and cleaner to apply, in my opinion here, but you can do this with the limit as h approaches 0 version. All right, so we're going to be using a as 0. So we're going to calculate from the limit definition f prime of 0. And we just plug in. Notice this simplifies rather nicely because f of 0 is 0. And f of x is absolute value of x. All right, so that's going to simplify to the limit as x approaches 0 of absolute value of x divided by x. Now, if you've taken good notes from the lectures here, you probably have it, if you've been numbering accordingly, within our lecture from the limit of a function. This was example 2, but flipped. In example 2, within that lecture, the limit of a function, we had this limit, the limit as x approaches 0 of x divided by absolute value of x. And we did see, definitely go back and rewatch, that that limit does not exist. Now we'll just do a quick overview of this because this is pretty much just the reciprocal, it's flipped. This limit that we're interested in, defining f prime of 0, also does not exist. Check in detail, check the limit to the right of 0, it will be positive 1, and check the limit as x approaches 0 from the left. That comes out to be negative 1. Now you have here your one-sided limits to 0. They both exist, but they're different, positive 1 and negative 1. Different one-sided limits mean the two-sided limit does not exist. So what we have just proved mathematically is this function, absolute value of x at 0, is not differentiable because the derivative does not exist at 0. All right, great. But what does that really mean? Well, let's look at the graph. The real reason we introduced this property of differentiability is it gives us some understanding of what's going on with the graph. And this will be something that we use later in the course to address and answer our long-term goal of graph or curve sketching. Now, differentiability is not only used for that, but that's at least a simple concept that we'll be constantly working towards that I will keep pointing out. All right. So let's get into what differentiability really means, not relying on the mathematical definition. The mathematical definition of differentiability is fine, something about the derivative at a point existing or not existing, but it's not really giving you any conceptual understanding. It's just a definition. So let's take a look at the graph of absolute value of x and see what's going on at that at 0. Now, take a look at the graph of absolute value up there. I modified it. It has what we're going to call a sharp point at x equals 0. All right, that's related to differentiability in some way, which we'll define clearly momentarily. The other thing I want to point out is this function, absolute value of x, at 0 lacks a single tangent line. In other words, at x equals 0, this function or its graph does not have a unique tangent line. Now we're going to just say basically a tangent line is the line that touches the graph just at one point. So take a look at that idealized sharp point on the graph of absolute value of x at x equals 0. There's two tangent lines that I sketched, and they both seem to be tangent to the graph, only touching that tip, the sharp point, and that's it. Now, just to make the sketch look as nice as possible, there's two tangent lines that I sketched. But you can probably see at that sharp point, there's going to be an infinite number of tangent lines if we try to use that idea of a tangent line being the line that just touches the graph at that one point. So what's really going on, what's making this function not differentiable, is the sharp point in the graph and the presence of multiple, technically infinite numbers of tangent lines here. They all have different slopes. All right, that'll play into this. Before we advance, the other reason we use the graph of absolute value of x to motivate this concept, you can build up the graph of absolute value of x as a piecewise defined function. Take a look at the right half. That's the graph of y equals x. What's the slope of y equals x, that line? +1. The left side of the graph, that's y equals -x. What's the slope of the line with the equation? Y equals -x. Think y equals mx plus b. The slope of the line on the left, y equals -x, that has slope -1. So what's happening is at x equals 0, the graph has tangent lines of slope 1 or -1, basically on either side, basically making this not able to have a single slope of the tangent line. Just on either side of it, it's different values, 1 and -1. You can kind of see that with our limit definitions there for the limits to the right and left of 0 being 1 and -1. All right, so let's advance. We'll go into a little more detail and elaborate on how a sharp point can be interpreted as a point of non-differentiability and the various other ways. Okay, so let's kind of hopefully give a clear answer to what differentiable really means. So I'm going to draw two different graphs. The first one there, some arbitrary graph, is what we would call a smooth function. All right, there's no sharp points. We're going to contrast that with the graph of absolute value of x on the right there, which is not smooth at x equals 0. All right, so we'll make the connection. Notice for the graph of that function on the left, if we take a look at a point there, just some random x value that we pick, 3, that function and its graph has a single tangent line at x equals 3, or the point with x coordinate 3. All right, now this graph is smooth at x equals 3, which would allow us to define and say that f prime of 3 exists. And recall our definition, we say a function is differentiable at a point A if f prime of A exists. So here, f prime of 3 exists. Graphically, there's a unique or single tangent line at that x coordinate. So we say this function is differentiable at 3. Graphically, the function is smooth at 3. Now, what's going wrong with absolute value of x at 0? Well, there's a sharp point in the graph, and there's the lack of a unique tangent line. A few seconds ago, about a minute ago, we stated that at x equals 0, there's many tangent lines at that point x equals 0 to the graph of absolute value of x. All right, so really what we're trying to understand here is that a function being differentiable tells you something about the graph being smooth, or if a function is not differentiable at a point, the graph is not smooth. Okay, and that is the important aspect I'd like you to take away. There is a definition, a mathematical definition for a function to be differentiable, but it's not as important as this concept of a function being smooth. So let's state it clearly. When we say a function is differentiable at A, graphically, that means the graph is smooth at A. A little bit later in our course, once we start to progress through other ways, shortcuts to calculate derivatives, and we get into something called the linearization of a function, we'll revisit this idea of what a tangent line, what differentiable means, once we have kind of some more appropriate tools, I'll say. All right. Now that we have a basic understanding of what differentiable means, a graph being smooth, a function could be not differentiable due to a sharp point, let's kind of take a look at the other simple ways a basic function could fail to be differentiable. All right, and the first way a function could be not differentiable, or a function could fail to be differentiable, is if the graph has a sharp point, like that of absolute value of x. Maybe it has a corner, or what we call a cusp. And all three of those graphs, at the sharp point, the corner, or the cusp, would fail to be differentiable. Everywhere else, those graphs are smooth, so those functions and graphs would be differentiable everywhere except the sharp point, the corner, or the cusp. All right, there's a second way, which we'll get into in detail momentarily. A function will fail to be differentiable at a discontinuity. So just to draw one example, here is a graph of a function with a jump discontinuity. This function would also not be differentiable at that point where the jump discontinuity is. All right, so we're starting to see there might be a connection between differentiability and continuity. We'll get into that next. And probably the kind of, I'll say, least often encountered, but still important to keep in mind, this is a little harder to kind of visualize. A function will fail to be differentiable anywhere there is a vertical tangent line. Now, I think by hand, what I sketched here for the third example, looks pretty good, but realize even if I drew this more accurately by hand, it's only a mathematical idealization. Now you might be thinking, does this define a function, this graph? Does it pass the vertical line test? As best as I can draw it by hand, we're intending it to. So this is a function, it passes the vertical line test. But what happens is just at a single point, the tangent line, as sketched there, becomes vertical. Now, what's the problem with vertical lines? Again, let's see how many of you really know your algebra. What is the slope of a vertical line? A vertical line, its slope is undefined. If you want to be a little more informal, you can say a vertical line has infinite slope. It's a non-numerical value. And we relate the concept, derivatives to slopes, slopes to tangent lines. So here we would say the derivative does not exist because the slope of the tangent line is undefined. So we get here another way for the derivative to not exist, making this another way for a function to be not differentiable with a vertical tangent line. All right, we're going to start to see some of these when we're dealing with graphical interpretations and questions related to being given a graph or asked to sketch a graph. There's some examples and questions relating to differentiability or non-differentiability. All right, so we'll see that within homework questions. Let's get to that briefly mentioned relationship between differentiability and continuity. All right, so here, this is kind of our first kind of new theorem, an actual official theorem that's important, in my opinion, in calculus or the calculus sequence. And the summary is that differentiability at a point implies continuity at a point. All right, and if we take a look at the theorem here, It says if a function is differentiable at a, then it is continuous at a. All right, so earlier we were mentioning something about a function, absolute value of x, being not differentiable. What this says is if a function is differentiable, then it has to be continuous. Mathematically, we say that differentiability is a stronger condition than a function being continuous. In other words, if a function is differentiable, it actually has some other properties. In this case, if a function is differentiable, it's also continuous. Now just be careful with what the converse would say. So this has the form of a logical statement. If P being the conditions, then Q being the conclusion. Be careful, flipping that, Q implies P is false here. This statement, if a function is continuous at A, then it's differentiable at A. That statement is false. The counter example, and in mathematics, it only takes one example to prove a theorem or statement false in general, is absolute value of x. The graph of absolute value of x at 0, or x equals 0, is continuous, but it's not differentiable due to the sharp point. So keep that in mind as the standard counterexample to this statement in red. The theorem is true. The statement in red is not true. It's false. All right, now the proof is short. I'll leave that to the discretion of your instructor. I don't think it's important for you, a student in Calculus 1, to know the proof for this theorem, but it is rather short. If you're at all curious, that's something you can definitely follow up with me on, but the proof is not something I would test you on. All right, so let's get to a related question here. Here, we're given the graph of a function, and we're asked, use this given graph of f to sketch the graph of f prime. Now again, this is another conceptually challenging problem. We're going to start to try to do this and establish that relationship between functions and derivatives and vice versa. But pause and give yourself a little bit of time to attempt this. This is one of the simpler examples on this type of question, hopefully preparing you for some of the more difficult ones in the homework. So pause the video and give yourself maybe 1 to 2 minutes to see if the concepts come to you quickly. We'll check in about 1 to 2 minutes. All right, welcome back. Now here, we want to think, how can we interpret derivatives? Well, we gave that question with 3 answers. A derivative is a slope of a tangent line. Now this graph is simple. It's built out of kind of 3 straight line segments. Some of the examples in the homework have a curvy function, so it's a little harder. But basically, we either try to find or estimate the slope of the tangent line to the graph of f at each point, and then we plot for f prime each individual slope. Now this one's simple. Those straight lines with this, pretty accurately drawn graph by hand there, we just need to calculate the slope of each of those line segments. That first one, going left to right, has slope 1. The middle line segment is horizontal. It has slope 0. And then the rightmost line segment has slope -2. Just use rise over run. We go down 2 units over 1. So this is a really simple function since its derivative only has 3 values. So we just split that up. We look at the interval from 0 to 2, 2 to 5, and 5 to 7, and the derivative has 3 different values, 1, 0, or -2. Now it's worth pointing out, due to the corners and recall we mentioned a function is not differentiable at a corner, the derivative doesn't exist at 2 or 5. And that's due to the corners at x equals 2 and x equals 5. So if we plot these three derivative values, we get the graph of our derivative as this simple but weird function. All right. Now, again, there's some examples in the homework that are harder than this, but this will hopefully prepare you for that. Just try to determine the slopes of the tangent lines and then plot all those slope values. All right, at this point, we're ready to introduce higher order derivatives. This is changing gears a little bit. And to put it simply, higher order derivatives are derivatives of derivatives. Now this will get really tedious currently because we only have access to the limit definition. So let's say f is our function. We already have our limit definition for f prime. It's the limit as h goes to 0 version, f of x plus h minus f of x divided by h. And we can reuse that. Now, instead of having f within that limit definition, to define the second derivative, the derivative of the derivative, we use f prime within the limit definition. So the limit definition of f double prime, it's a limit as h goes to 0 of f prime of x plus h minus f prime of x, all divided by h. Now, I'm not going to spend too much time on this. Honestly, it's not important, in my opinion, to go into detail. Currently, we don't have access to any differentiation rules yet. We only have the tedious limit definition. But I would like you to try one example. So if you want, pause. But this is not an important example, but it kind of relates these concepts, higher order derivatives, back to a computationally challenging question. All right, so take some time maybe after to attempt this. You're given a function, f of x as x cubed, and you're asked to find the second derivative, what we would call f double prime of x. All right, and there's some work here just for guidance. This is a fairly tedious problem because you're applying basically the limit definition of the derivative twice, and it's just not really not useful for applications within science and engineering to keep applying the limit definition. It's not definitely not at all time efficient. All right, so we're going to revisit this idea of higher order derivatives once we have access to the differentiation rules. Now we're going to close with some notation just to get comfortable. So we have our usual prime notation in order. That's the first, second, and third order derivatives. We represent the order by the number of primes, standard notation. We could write it as y for our function. Then we would write our derivatives as y prime, the second derivative y double prime, third derivative y triple prime, so on and so on. And there is a way to express higher order derivatives in Leibniz notation. That's the notation dy over dx. The second derivative, it's the derivative of dy over dx. Now it's a little awkward, but dx of dy over dx, it looks like we're multiplying. So we're going to write that in shorthand notation to be this. Then we can express a third order derivative in Leibniz notation as that. All right, now just to close, we're going to give the interpretation for higher order derivatives. Start with position. The first derivative is velocity. The derivative of velocity, that's what we call acceleration. Now we're going to revisit this once we get access to our shortcuts. Hopefully you're thinking, what are these shortcuts you've been alluding to? Well, We're going to start those in the next lecture.